So I'm going to talk about a very recent work with my postdoc advisor Xin Guo and Anren Hu. So we are going to talk about a mean field story for the Stackelberg game and give a new perspective from optimization and do a rough sensitive analysis. We're going to first have this model setup and then talk about this optimization framework here. So the first is what is the mean field Stackelberg game? To introduce it in general, so we have two types of player, the leaders, and since we're in mean field type, so we have many followers here. And for the Stackelberg game, basically the leaders will propose an action to the followers. According to this action, the followers will play their own game, basically their own Nash equilibrium, and then this their decision will finally affect the reward for the leader here. So there are many real life examples. One quick one popped into my head is like when we are going to organize such a nice meeting here. So the leader, as our organizer, should propose to the potential speakers like the dates and place we are going to have this conference, and then all of us will decide whether we are going to attend it in person or just on Zoom. And according to that, they will finally decide which place and time we are going to have this conference here. And also in other applications, we have like principal agent problem and optimal taxation problem, optimal auctions, and security games. So there are also many nice theoretic framework for this mean field Stackelberg game, and I think we're going to listen to one of them from Professor Huang this afternoon, talking about like the mean field Stackelberg game and using the master equation in a theoretical framework. But for now and for this talk, I'm going to focus on a learning-based setting, which is a banded setting. Then that is very similar to what Sari talked yesterday, and also Renee and Matthew talked. So we are going to focus on finite discrete time and finite state and actions. So basically the notations here is we have time t and state s, a for leaders and followers, and mu t would be just the distribution of the followers state, since we are only focusing on like many followers rather than many leaders here. And the reward function, as I said before, this will depending for the leader, it will depend on the state of leader and the action of the leader and the distribution for the followers. And also for the followers, the reward will also depending on the action for the leader that the leader proposed to them. And for the transition probability, it's like the same thing here. So it's more like a model-free setting, since we only have this transition probability here. So there are different goals for the leaders and followers. For the followers, they need to determine the choice of AT at each step of T by the policy here. And also, so this would be more like a parameterized mean field game, since the leaders will propose them an AL, and then given an AL, the followers will play a mean field game here, parameterized by this AL. And this maximization here usually means the Nash equilibrium. And in our setting, we are actually focusing on epsilon Nash in several layers of reason. One reason is that like many people are okay with like having a little bit error here. And also a more reasonable thing is that in general, especially in the learning cases, we don't have an exact access to the model. We probably have some error here for the model. In the sense that we don't know the exact reward, and we don't know the exact transition probability. So in the end, this will give us an epsilon Nash rather than a Nash equilibrium. And of course, the final Nash equilibrium here will be depending on the leader's action here. And a natural thing here is that, so if we are considering epsilon Nash, and even if we are considering just Nash, so some non-uniqueness problem will show up, meaning that the followers might have multiple choices for their final actions and for their final policies here. So this basically arises some problems for the leaders. So basically for the leaders, there were different type of leaders, saying that they have optimistic leader and pessimistic leaders, and they want to maximize their own reward with respect to the best cases and the worst cases. Meaning that if we define the leader's reward by this V, there are several different definitions for this V. And in this talk, we are focusing on the pessimistic one, which meaning that the leaders will minimize over all of the epsilon Nash equilibrium for the followers, and then the reward function would be the minimization of that. So for the leaders, of course, the goal would be finding the best AL star, or at least this best AL star will not, the AL star they find would not be too far away from their best choices. So for this type of problem, basically the goal for the leader would be the final objective for this Minfield Stackelberg game. And in this talk, we are basically present an optimization framework in the sense that we don't use the usual fixed point part of view for the Minfield game, but we are considering this whole type of thing since we are facing a kind of simpler settings where we only have finite state and finite actions, and we will consider this whole problem in one general optimization problems here. So the Minfield framework basically is the feasible way to find the best response for the best action for the leaders. And actually, if we are without the Minfield game, there are already some results by and he just consider a constraint MDP problem. But in our case, to find this optimal AL and the optimal B, we're saying that this will be equivalent to a certain optimization problem with like smooth enough constraint here. The starting point for this optimization problem is quite straightforward. Basically, if we put this mu L and D and mu as the occupation measures, meaning that we consider this mu and D and mu as the measure for the state of the leader and the measure for the state and action for the followers, and also the state of the distribution for the state of the followers, then we will naturally have this kind of objective with like just the expectation of the reward for the leaders, and also with the constraints that for the measure they should satisfy the transition probability conditions, and also for the followers they probably need to they must satisfy that the measure they are choosing is epsilon Nash equilibrium, in a sense that have this one, but in a sense that their expected reward will be larger than the best reward with an arrow epsilon, or at least larger than the best reward with an arrow epsilon, and the best reward was under the constraints of this mu. So this optimization problem is good enough, except that for this J mu star, we don't have an explicit formula for this J mu star for different mu's. But the good thing is that for this J mu star, we can again applying some optimization formulations, in the sense that for the J mu star, we can use KKD conditions to deal with the J mu star, and then write the second layer of this problem into one whole optimization problem, in the sense that we change this J mu star just by some other conditions using this KKD condition, but adding some more constraints and more variables X, Y, Z here. And the good thing is that this is a new framework for understanding this Minfield game, at least with finite state and finite actions, and all the constraints here, as long as we have some nice assumptions for the reward function R and for the transition probability P, then this will be a smooth, at least there will be a smooth constraint, and there are plenty of tools in the optimization series to deal with this problem, at least having some like local convergence results here. And for the second part, which is the sensitive analysis, in the sense that in the real life, especially in learning type of thing, we cannot have access to the true model, and what we only get is somehow some estimator R hat and R hat P hat that it might be close to the real model here. And if we denote this V hat as the corresponding problem, then basically we can only have access to this V hat, or have like to solve this problem under this V hat here. And we have somehow a complicated sensitive analysis, since this is a very rough one, but we can still get it from our optimization framework, saying that if we want to get as close as we want in the beginning, in the sense that we want to have this AL star being at least close to the maximum of AL star, and then we will have two different arrows. The first arrow epsilon we can choose as small as we want, and for this delta, this will be some small term, at least some like the same order term as the delta close estimator we choose here. And this actual AL star, we will choose this one to be arc max of this V hat with actually a little different Nash equilibrium, in the sense that we will have some relaxation for this Nash equilibrium, and we will have an epsilon prime here. And one fun fact for this is that even if we are working with the as long as we are working with the estimated model here, then choosing this V hat of like 0 AL will not generally work to have such nice results. And we have some like counterexample for that, just saying that this if we just taking this v hat with the same epsilon Nash, then this type of thing will basically fail. And yeah, thank you. And here is the whole thing for this.
Thank you. Are there any short questions?
So you just parameterize the policies as a sequence of vectors, right?
Sorry, what?
You use randomized policies.
Yes, with randomized policy, indeed. So we assume this AT can be some policy in the sense that this AT can be some, we choose this AT in the distribution pi t given ST here. So it's it's more like a relaxed control in the sense of like a classical mean field game here.
Yeah, so essentially in the end, it's like a static problem. You just optimize in an abstract space.
Yes, indeed.
I think the main issue is that by this approach, you will not have a time consistency because it's well known for Stackelberg games. Mm-hmm. It has this problem.
Yeah, probably we'll face several problems, but here we for the leader's action, we actually don't have any. So basically, this leader's action will not depending on the time. Here we will have an like time independent leader's action in the sense that the leader's action will not change during the time. So in this like simpler setting, somehow it can solve a little bit about this question. But if we are working with actions depending for the leader's action, if it will depend on the time, this might be even more complicated and it's even harder to have a feasible way to solve it.
Yeah. Thank you.
Thank you. Thank you for the question.
So let's thank again Jiacheng.